Have a day, as they say. Oh, that is a nice starting point. Have a day, as they say. And then I take, of course, off my glasses so that I can see the screen better. All right? And this is a little bonus video as part of the introduction, Geology for Engineers. And I'm going to demonstrate a little bit about my specialty, sedimentology. And we do that by an experiment. There it is. So, sedimentology involves transportation by wind or by water. And water and wind flow in a river, on the bottom of a sea, in a lake, at a certain rate, the flow rate, which is an expression of the kinetic energy of the water. And that kinetic energy, the higher it is, the more sediment it can carry. The higher the sediment particles that are dragged along by the water or the wind, right, increases when the river flows faster, if the waves are higher, right? Very simple. So when the water flow decreases in speed, then gravity will pull out part of that sediment load, and it is being deposited on the bottom of the lake, on the bottom of the sea, on the bottom of a river. Right? I'm going to demonstrate that. We need a sediment source. Here is a sediment source, my Rogers sugar. You see it? Okay. So now the water slows down and it can no longer carry all the sediment, and what happens is sediment falls to the bottom of the river, the lake, or the beaker in our experiment. Now, sugar is not necessarily a common sediment source. In fact, sugar is not a sediment at all because it's formed from and produced from beet, for example, or sugar cane, right? But it shows you the particles that are sinking, that are being deposited on the bottom of the beaker. And normal on this planet, we have various sediment sources. Most often it are mountains that get eroded away by ice or by water and weathered by the wind, and the rock is being broken down in small particles, small sand grains, small clay particles, and so forth. And they are then being picked up by the water or the wind and transported to a point of deposition. There, the kinetic energy has dropped and the sediment is falling out of the water to the bottom of the beaker. Or the sediment is falling out of the wind and falling to the bottom of a desert. And that is as simple as it gets. Oh, by the way, there is another form of deposition. And that is the sugar can dissolve in the fluids. And then if the sugar concentration gets too high and temperature changes or pressure changes, then the sugar can come and precipitate from the water onto the bottom of the beaker. Right? Also, when we have a heating up of the climate, you can get more evaporation of water, and the concentration of the salts dissolved in the water, right? Like calcium, which forms a deposit, carbonates, on the bottom of a lake. Or salt. When the water gets really heated up and gets really saline, as we call that, you can get salt and gypsum dropping to the bottom of the beacon. They're coming out of solution, precipitating. And if you bury gypsum, right, underground, under an other sediment column, the weight which can be quite substantial, then it gets compacted. We call it, right? And then it can be transformed in something we call anhydrite. So anhydrite is basically dehydrated gypsum. Wow, now we learned something, right? Now we're going a little bit further, because we also know that some materials dissolve, some gases can dissolve into water, into fluids. CO2 is a very famous example thereof. But CO2 is a strange material because the capacity of dissolve something in a fluid is called solubility. The solubility of sugar, the solubility of salt in a fluid, in this case water. Also the solubility of CO2 in the water. The strange thing about CO2 is that it doesn't increase, the solubility of CO2 does not increase when the fluid gets warmer. You can dissolve more salt in water if it heats up. The same for sugar. But with CO2, it's just the opposite. The warmer the water gets, the less CO2 it can contain. And you can see that in today's ice ages. We're living in a period where we have cyclical ice ages and inter-ice ages, right? Glacial and interglacial periods. And they stretch out over thousands of years. So typically, the CO2 content during the coldest periods of an ice age is very low because it's all been dissolved in waters and in frozen marshes like muskeg, right? And there it is absorbed. In fact, it can be so low in CO2 in our atmosphere during ice ages that it inhibits plant growth. It's not only the temperature that prevents plant growth, it's also that we have a very low CO2 content. Now you can go back into history, geological history, go back 150 years ago when during the Jurassic, the dinosaurs roamed the earth. It was warmer then than it is now. But there were no ice ages acting up at that point in time. And neither did it do later during the Cretaceous, right? Where we still had a lot of dinosaurs around until the end of the Cretaceous, and they speculate that the Earth was hit by a meteor and somewhere landed in the Gulf of Mexico, created something akin to nuclear fallout, and really that was what extinguished the dinosaurs. But before that, the dinosaurs were happily around, farting around on the planet, and plant life was very abundant. And we have even an older period that we call the Carboniferous. That is when most of the land was filled with plants. Most of the continents were overgrown with plants. And we had enormous amounts of coal deposits being formed. That's why that period is called the Carboniferous. Right? And during these periods, there was abundant CO2 and the climate was a lot warmer than it is now. So, going back to the glacial cycles, we have very low CO2 and low water levels. Like at the end of the Ice Age, the last Ice Age, 10,000 years ago, you could walk from Amsterdam to London, where now we have the North Sea. I have to control my hand. It starts to move around like crazy when I get excited. Well, I'm a Dutchman and I like the idea that I could have walked to London, would have saved me a train ticket or an airline ticket, right? Well, but what happened was that about at the end of the last ice age, temperatures started to heat up. And that might be for various reasons. And I can speculate about that, but that's not the point. The point is that the temperature heated up, and thus we start seeing the permafrosts, the muskox and so on, to melt and release CO2. We saw the seawater and the river and the lake waters all warming up and releasing CO2. And we see that happening every glacial cycle. And the more CO2 is being released, right, the better it is for the plants. So then the plant life starts to increase. And some biologists think that we need a certain amount of CO2 in the atmosphere to promote life on Earth. You need definitely more than what we had during the ice ages. And then after that, plant life starts to flourish and humans start to evolve. And in fact, some scientists say that, and you have to realize science tends to extrapolate to extremes. So don't believe every extrapolation. So the scientists, the biologists claim that if we would stop at the levels of CO2, say that we had during ice ages, then life on Earth, in particular animal life, would become extinct over a mere 2 million years. And it's only mere because 2 million years is a fraction compared to the age of this planet, right? Which is 4.5 billion years. Big Bang, boom, right? And over all those billions of years and hundreds of millions of years, our atmosphere has evolved. In the beginning, the planet was not much more than a bunch of gases and some molten materials, and it has evolved to what it is today. So there is always change in this planet. And I know humans are afraid for change. And that is why we talk about climate change. It's so scary. No, it's a normal process. It has been going on for several billions of years. And so what is going back to the glacial cycle? So at the end of the glacial cycle, we released CO2 in the atmosphere. And the warmer it gets, the more CO2 gets released. So it is not, or at least that is what many geologists doubt now these days. It is not that that temperature rises because of CO2. No, CO2 increases because of rising temperatures. And that is quite a different story than you may have heard, right? And typically these glacial cycles, they reach a peak temperature and then there is a turnaround, a flipping around. We're going from getting warmer to entering a new ice age. And these processes take thousands and thousands of years. So it is not, although we are now pretty close to those peak temperatures where things may change. And scientists, geologists in the 1970s already said, we might enter a new ice age. And even if they did, if we really reached that tipping point, then it would be still thousands of years before we had as much ice on the planet as we had during the last ice age. And to show you how important those ice ages are, is look at my residence area. I live in Calgary, Alberta. And 10,000 years or 15,000 years ago, during the peak of the last ice age, there was an ice cap above me, where I'm sitting now. 1,500 meters high. That's what scientists have calculated, based on isostasy. And we'll go on into isostasy later on in the real introduction of the geology course. Okay? And now all that ice is gone, right? And we are approaching another point in time where we may be flipping and going back into another ice age. And 15,000 years from now or so, and I don't quibble about a few thousand years, to be honest. 15,000 years from now, my residence may lay below an ice cover, an ice cap that is again 1,500 meters thick. And the erosional powers of those glaciers are enormous. You can see it today in areas like Greenland or in the Columbian ice fields. And we saw that happening also over the last 10, 15,000 years. It's not only that sea level rises from the ice ages from a spot that you could walk from Amsterdam to London, and then today you have 100 meters of water above it, which is called the North Sea. It's also here in the mountains, because glacial periods and water from rivers are the main sculptors of our mountains. They cut out enormous valleys and they remove enormous amount of sediments that are being transported by the rivers towards the sea. And that is the depositional process. And some is left behind on the bottom of rivers and fluvial valleys, and some is left behind on the bottom of lakes, and a lot typically is being deposited in the sea. And an example of that, to give you an impression, is that I think it's 10,000 to 15,000 feet thick sediment accumulation. So that is about 4,000 to 5,000 meters of sediments, if you metric, that have built up the Mississippi Delta in the Gulf of Mexico. Yes, we're talking about very large numbers of sediment accumulation, and very, very complex, because it's a process of erosion, say during a storm, or during the winter season, or during the tide, and deposition, the supply of sediment. And this can be a 2-week process. It can be a process of many of thousands of years. That is what makes our planet so bloody complex, right? And when we go into interglacial areas, times when the temperature increases, so does the CO2, and it's good for plant life. And so what we see recently is that areas like the Sahara have grown in forest cover. The Sahara is shrinking, and we see the plant life increasing on the planet. And it's not only due to the planting of trees programs, because that is also an important contribution, I think, but it is more even so as a planetary process, because that we're reaching highest point of our ice age. And I don't know when the flipping point will be and how close we are to a critical temperature in the atmosphere. But once it flips, we're going back into a period of glaciation, big accumulations of ice, but very tough for all of us to survive. But it is thousands of years from now, not tomorrow. Okay, I think I've said enough about all these topics, and I hope that you have a better understanding of one part of geology, the study of sedimentology, where we study how deposits like sand, carbonates, limestones, reefs, rivers, and the sea, how they are being formed. Okay, and we'll talk more about that during our course.